Yeah, so this performance RNN works quite well. I think this is a really great system. The problem with it is that it tends not to develop ideas, sort of high-level ideas over a long period of time. So it sounds good like within 10 seconds, but it doesn't really go anywhere in the music. So this is the problem of learning long-term dependencies, which you might find out some more about. Now I'm going to do a few examples for the rest of this this lecture, the final half an hour. And I just want to say, if you're interested in playing with RNNs, I'm happy to talk to you about them this afternoon. I've got a website called creativeprediction.xyz, where I've got a lot of tutorials in the form of Jupyter notebooks, Python Jupyter notebooks, that you can try out yourself if you're interested in these. But I'm going to give these as demos from live coded demos right now. So now we're going to do a character generation RNN, just as I showed you before how to do theoretically. Now we're going to do it in practice using Keras. And the text that we're going to use is a list of all of the episode titles from Star Trek. So we'll just have a look at that list. Sets, Star Trek episode titles, and maybe can't see very well. Here's a list of the Star Trek episode titles: The Man Trap, Charlie X, When No Man Has Gone Before, etc., etc. Now there's not that many titles in this list. Let's have a look at this in Python. First I'm going to do a lot of imports, as you generally do in Python. And I'm doing this in Keras, so you can see I'm importing the Keras sequential model. Then a bunch of layers: dense, activation layer, LSTM, that's important, we need LSTMs for this. Dropout, I'm going to use this RMS prop optimizer, and a few other utility functions. So now what I've done is open this file, Star Trek episodes, and I've printed out the corpus length. So this is 11,000 characters, which is not very long for a text corpus, but I just wanted to train it for you right now, so we're doing a small corpus. The first thing I do here is take all of the characters in my corpus and find all the unique characters. So there's actually 49 unique characters in my corpus. And that means that what I'm going to do in my RNN is make it so that the dimension of my categorical output will be 49, and my input will also be of length 49, right? I'm not going to waste my time learning to produce characters that aren't in the corpus. But if you had a bigger corpus, it would probably have a few more characters. Just done a little bit of figuring out of how many characters there are in each title, and I can find that the median length is 13. So I'm going to train this to produce with inputs of length longer than that, so that at least it has in each input one whole title, or the best that we can find. And here's 2 dictionaries that I produced to create a integer index for each character in my corpus. So I've transformed each one into a int. Okay, setting up the training data. This is, I realised that was probably too small. Anyone see now? Yeah, probably. So just as I said before, we take our corpus and we cut it up into X's or inputs and Y's outputs. So the inputs will be short sentences and Y will be the next character. So I do a little bit of code here to cut this up. This is kind of in one of the Keras examples, but we've done a little bit of extra work just to make it a bit more clear. So here's now I've figured out that I've got 3,000 input sequences, 3,660 output letters, and here's the first example: the Man Trap, Charlie X, and where N, and the final letter is O, because the title is Where No Man Has Gone Before. So my next step is going to be to change this to one-hot encoding. So I take each letter and transform it into a vector where the number at the index corresponding to that letter is 1 and everything else is 0. I go ahead and do that now. That doesn't take very long. And now I've got 2 NumPy arrays from my data. The X data is an array where the first axis is 3,660, that's my number of examples. Second axis is 30, that's the length of the sequence. And the third axis is 49, that's the number of integers I've got, or the number of independent characters I've got. So that's the length of my one-hot encodings. The Y shape skips the 30 in the middle because they've only got length of 1. let's have a look at one of these examples. This is the first X example. I just want to just take the very first letter. So I've got a NumPy array of type Boolean with 48 falses and 1 true in there. That's handy. Okay, now we're going to create our model. This is one of the funny things with these simple examples in Keras is that you tend to do a lot of work to just set up your data and then about 3 lines to create your model. So my model here is this line, sequential, that makes my sequential model. 1 line to add a layer of LSTM nodes, and then 1 layer to add the softmax layer. So that's it, 3 lines of code to make a neural network. It seems too easy, but that's kind of how things go in Keras. There's a lot of details inside each of these objects. If you're interested in more details, you can break into them. If you want to work in TensorFlow, that's a bit more kind of heavy duty. You've got to do a little bit of extra work to build these layers, but still it's generally not that much work to create the neural network. All the stuff around it, creating the data, doing the evaluations, is generally takes much more code. So this is a sequential model from Keras, and I'm going to add 128 LSTM units at each sequence step, and I'm going to unroll to this length, max len, which is 30. So in Keras, you have to tell it before you make your neural network how much you want it to unroll, which is a bit annoying. In TensorFlow, there's a way of not doing that, but that must be the way it happens in Keras. Then I've got to add an extra layer because the output of my LSTM layer is not going to be 49 letters, it's going to be 128 numbers from each of these LSTM units. So I need a second layer, just a regular feed-forward, non-recurrent, dense neural network layer to transform from the size of my LSTM layer, 128, to the size of the set of characters I've got, which is 49. So I've said model train dot add, the dense layer with the output dimension is the length of my list of characters, which is 49. And the activation is going to be the softmax activation function, so that I get my probability distribution. So that's my network. The last step when you're making a neural network in Keras is to do this compile function. And when you compile it, you have to tell it what loss function you want. So I've got the categorical cross-entropy loss, just as we saw before. And then the optimizer. The optimizer is a function, or a relatively complicated algorithm that knows how to do backpropagation and knows how to adjust the weights in each training step. So for this one, we're going to use RMS crop, which is a common choice. Another common choice is one called Atom for recurrent neural networks. But for some reason I'm not choosing that today. And then I'm going to also run this summary line, which will just tell us what we've done. So when I run summary, it gives you a summary of what's going on in your neural network. First layer is LSTM units, output shape. That none is there because of the length, the batch size. We don't have to give it the batch size now. We can give that later during training. And that LSTM that LSTM net layer has 91,000 parameters, so it's got a lot of parameters. Second layer, dense layer, just to get us to our 49 length 49 categorical distribution. That only has 6,000 parameters. So you can just see right here how many more parameters, even though this should be a smaller layer anyway because it's got a smaller output shape, but it's got way fewer parameters than the LSTM M1.
What does parameters means?
That's the number of weights.
Number of weights?
Yeah. So one parameter is one weight in one matrix. So if you have a feed-forward network and your input is 10 numbers and your output is also 10 numbers, then you have a weights matrix, which would be 10 times 10. Once that's 100 weights, then you have to have 10 biases, one for each of your outputs. So then you're going to have 10 times 10 plus 10 equals 110. So let's just work this out. This dense layer here, what's the shape of its input?
That 1 to 8.
Yeah, 1 to 8. So thank you for looking at the screen, everybody. What's the shape of its output?
49.
49, exactly. So how many weights does it have?
1 to 8 cos 1 to 8.
Well, it's 1 to 8 times 49. That's the size of the matrix, plus biases for the one bias for each
1 to
output.
8.
That's 49 because that's got to be the outputs. 6,321. Is that correct? Yeah. Okay. This is a true test. In any master's thesis to do with deep learning, if I was assessing it, if I wanted to be a jerk, I would ask someone why they have that many parameters in the neural network and ask them to explain it. I think it would be quite hard for some students, but it's good to know. Our LSTM layer, I'm not going to bother going through that now, but it's, we can do that later. Okay, now when we sample from this model, as I said, you need to use a sampling function to go from your probability distribution to a letter. Here we've written one up. This sort of goes through the sampling process in full, but basically we're using a function from numpy, np.random.multinomial, to create sample from our distribution and give us an index of which character we want to choose. So the trick with this is that I've also got this extra input called diversity, which is often also called temperature. So if you've got a probability distribution here represented by a plot, sort of somewhat misleading plot because it's all the dots are connected, you can make it more diverse by sort of artificially boosting up the unlikely options and reducing the very likely options, or you can make it less diverse by boosting up the likely options and reducing the unlikely options. And if you wanted, one reason to do this is to make your neural network sort of make more creative choices, choose things that are less likely, which could be useful in text generation or music creation, as I'll show in a minute. Here's our sampling function. I got some text here for generating sequences of text. This is useful. And now I'm going to do the training. Training in Keras. You only have to do one thing, model.fit. So how easy is that, right? Neural network, we can do it in an afternoon. Learn everything you need to know. Exactly, it's funny because it's so untrue. When we run this line of code, it's going to take our model and start applying the data we prepared earlier, x and y, containing our input data and our expected predictions. It's going to take batches of our input data of size 128 examples at a time. It's going to go through all the data 50 times, that's what epochs means. And I've got this thing called callback, which is a function that the training process will call after it goes through all of its data each time, after each epoch, and that's going to print some output from our network. So this should be fun. We can see how it works by running it. Yeah?
Batch size depends on your input, or it's just random number?
Batch size depends on many factors, which we'll go into later, but it's how many bits of data are taken at once and treated by backpropagation simultaneously before making weight updates. So after each epoch, you can see I get some text out. This is the text my system is generating. Does this make sense? No. I think in this epoch 5, it's learned how to write the. So there's lots of titles that have the word the in them, the something. So it can do a few of those. Epoch 6, still pretty boring. Epoch 8, a few more of those. Now it's starting to sort of get the correct length for each of these titles. It's putting the learned how to use the carriage return character to make things that seem like they kind of would be a sort of title, but the text is still nonsense. 12, epoch 13, hopefully, yeah, the loss is going down. 14. Oh, epoch 15, this is important. It's learned how to say part 1. A lot of Star Trek episodes are 2-parters, so it's very important that it knows how to say part 1 and part 2. Ooh. So now the problem with this is that I've given it a text corpus where almost no words are repeated, because Star Trek titles are like made up each time, like Charlie X. There's no other title that has Charlie in it, and probably no other title that has X in it as by itself as a word. So it's going to be quite hard for this neural network to learn anything useful. But we can still have fun with it. Lands Part 1, Fours in the Aldman. That could be possibly a title. The Umif Fiction. If only it hadn't misspelled fiction, it would almost have been titled The Wayuna of Hitcore. There's possibly you could write a script about that. So there's definitely learning going on here, and you can see our loss function is going down. 48.41. Pontes, Deet of Entei. Now we'll see, let's skip ahead and see how it's going. You can see it's going fast. I thought for deep learning, you have to go slowly, right? What's your question?
What's that seed?
Oh, the seed. Yeah, so when I generate my text each time, this neural network is unrolled to length 30 to produce one letter output. So to make it generate some text, I have to start with 30 characters, make it generate the next one, then add that to the end, take the next group of 30, add to the end each time. You see?
Yeah.
So in Keras, once you've chosen to unroll a network to a certain size and done that compile action, that's how far it's unrolled and will never change. But I'll show you a trick how to get around this in a minute. So we do need to have a seed of 30 characters to get it started with each generation, generation step. Yeah, so it's done now. Why was this so fast? It's not because my computer is good. The text corpus is small. Normally in deep learning people use huge corpuses of data, and they often use much bigger networks than 120 LSTM cells, right? I had like 100,000 parameters. Normally in big deep learning networks, question?
Isn't Jupyter the web application?
No, this is running on my computer. Yeah. This is still, it's fast because it's a small network, I'm not using much data, and I'm just training it in a sort of cheap way. So it's many of your models, if you're using big networks and a lot of data, would take a lot more time. But this is certainly doing okay. So here we are at epoch 50, and I still really have nonsense, but most Star Trek titles are nonsense anyway, so I don't consider that to be a loss. We can have a look and see how it was training, just by plotting the training loss over time. It was going down steadily. There was kind of a hiccup around epoch 38, where it, for some reason, went higher. It's difficult to know why. Neural networks is sometimes a bit of a bit difficult to work out. Now I'm going to show you a way of getting around this seed issue. So what I said was, once we've unrolled this to 30 characters, we have to provide it with 30 characters just to get with one character input. But in future, what I'd like to do is have a neural network which I trains on in that method. It's got 30 characters input, 1 character output, but for generating text, I just wanted to use 1 character input and 1 character output. So we can do that by creating a slightly different model, just a model just for decoding, where my batch input shape is just has length 1. Here I've got a new model dec, and it's going to have exactly the same layers, LSTM of size 128, 1 dense layer. I'm compiling it just the same, and then rather than train it, I just copy the weights from the other model dec.set weights, model training.get weights. So it's just moving the weights from the other model across. This makes it much easier to generate some text. So this generates text much faster than the other one, and it's the trained model. Now I can start to play with this diversity measure. If I make it very small, let's see what happens. That doesn't seem to make much difference. Very, very small. This actually doesn't work. It's starting everything with the part 1. It's only taking the most likely letter in any choice. Maybe it's more fun if we actually make this bigger. So I'll change it to 2.0. Now it's producing much longer words because it doesn't ever make the choice of putting the spaces. Comes up with some kind of untrained information. Yeah, okay, I'm going to show you another example before we stop. one extra thing, if you want to play with deep learning and you don't have a big gaming computer at home, you might be wondering, what am I going to do? I need GPUs to do deep learning. Well, you can use GPUs online, as was foreshadowed by my friend over there at the back. We can use Jupyter Notebook and Python Online. One way of doing this is to use Google's co-laboratory service, colab.research.google.com. This lets you open up an IPython notebook file, a Jupyter Notebook file, and run it with a GPU attached in a virtual server, which is a lot of fun. So I'm going to do the same thing. And now I'm running my code online. What I want to show you here is just a slightly better model. Instead of using one LSTM layer, I'm just adding an extra afterwards. So there's my first layer. Still layer size 128. And I'm going to add a second layer of LSTM cells, and then my dense layer afterwards. I've also done a trick here of using this thing called an embedding layer at the start, which means that I don't have to use one-hot vectors, because I hate making one-hot vectors. I prefer just to not. Probably someone could do a project in telling me why this is a bad idea, but I need to see the evidence. And at the moment, the convenience outweighs any potential reason why this is a bad idea. So let's look at my new model. This has way more parameters, 275,000. That's because I've added two big LSTM layers, 131,000 parameters for each one. And then at the front I've got my embedding layer, and at the back I've got my dense layer. So these ones, that hasn't changed. This is new, and then I've got an extra LSTM layer causing this big expansion in parameters. Training as before. I'm just going to make it train faster. If you're on a GPU, you can make your thing train faster just by making the batch size bigger, because it does those batches. It takes 256 examples and does them in parallel. So you can run a lot of things much more quickly doing it this way. Maybe it won't train so well. Oh, we'll see if the answer's in a minute. 8, 9. How long is this going to take? 3 seconds times 30, 90 seconds. I can wait 90 seconds. I'll drink some water. This is the fun of deep learning, just watching a loss value go down over time. It's many hours I've whiled away here in the Robin Labs. The previous master students know what I'm talking about. Just watching loss values decrease. Ooh, 2.4.40. 2.37, wow. The drama, will it crash? Will it complete? Will it be good even if it completes? You're doing advanced AI now, so you'll all know about this soon. Okay, we're done. 30 epochs. We can plot our loss function over time. It goes down, that's good. This, you can see it seems like it could keep going down, right? So probably I could do more training and get better results, but I can't be bothered right now. So you could maybe go to 50 epochs or 100, and probably you want to stop training when your loss value kind of flattens out. I'll save it, why not? Save model. Now I'm going to, as I showed you before, make another model for decoding. Same model. Did it load the weights? Yeah, it did load weights from the file. And I make a sampling function. And now I'm going to sample, hopefully it works. Oh, that was very high temperature. No, don't look at that. So this one, because my decoding model just takes one input at a time, I can just give it a single letter, A, and start sampling outputs from it. So this one's not that great, but maybe I can reduce the temperature a bit and get something more sensible. 0.6. Yeah, the Sol's Folks Magus. Increasing the temperature, maybe to 15.0. We should get some nonsense. Anyway, the point of this example was, rather than train the best text generation network ever, but just to show you that you can do these things either on your laptop or online. There's plenty of options for doing deep learning without having to have access to giant amounts of GPU resources. And this Google Cloud Laboratory is one of the better ones. Now, I've got about 5 minutes left, so what I'm going to show you is a musical example. Haha, because I like music, and because I like it, you all have to watch it. So, music's complicated, just like text, but there's a way of representing music, particularly melodies, just as a sequence of categories, just like in our character level text representation. So here's our simple music representation. This one's running on my laptop as well. Each note is going to be a number between 0 and 129. If you know anything about these digital musical instruments, keyboards and stuff, you know there's this thing called MIDI. MIDI is a standard for encoding notes on a piano as they're coming in. And MIDI lets you have 128 notes, so a number between 0 and 127 are these note values. So in my music representation, if you've got a number between 0 and 127, that means play a note with that MIDI number. It's sort of a note on, putting your finger down on the piano. If you get the number 128, that means stop whatever you're doing. And if you get 129, that means no change. So if your finger's down on the piano, you leave it there. And if your finger's already up, you don't do anything and you still get silence. So these numbers are going to be coming by at a set rhythm, and we're going to call that rhythm 16th notes. So that means 16th of a bar or quarters of a beat. So here's a standard melody converted into this format. There's the musical notes. If anyone can read musical notes, they could tell me that that's A above middle C, which is this MIDI number, 69. Then for the next three 16th notes, I'm making no change because I'm holding down that A above middle C. Then I hit it again, 69, da, da, 2, 3, da, da, 2, 3, 4, da, D sharp, 66, da, 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 end. So this is a very simple representation. If you want to look at more musical RNNs, you should check out Google's Magenta project, which has some great examples, but this one is focused on simplicity and clarity as an example that I can literally give in 5 minutes. So now I'm going to just run this bit of code which has all the functions I need to convert MIDI files from my computer into streams of these integers. Bit of work I did before over summer, getting these to work. These are all a bit wrong, so if anyone wants to do it as a project, I think Torgrim has been working on these or looking at these a little bit there. They could do with some improvement, so it's up to some clever students to figure it out. Now, just to prove to you it works, I'll load up a MIDI file from this famous Australian song, Waltzing Matilda, and this gives me this output. There's the notes from the MIDI file, here's the integers, and there's the notes again, and if you can read music or just use your eyes, you can see that this is more or less the same. So it works. The input equals output under this transformation. Now I'm going to skip making the data set. I'm going to start loading up my RNN. I've actually used a rather small data set for this RNN, and the data set was all of the music from the Legend of Zelda video games. So I just Googled MIDI files, Legend of Zelda, and downloaded a big zip file. Then I open each of these melody files and extract just the melody or the first voice, which may or may not be the melody. That may make sense, it may not make sense. Tell me if I'm doing it wrong in a project. Then I do some work here to slice these into examples, just as before. And I've got 122,000 examples of length 30, same as before, and the Y's is just 122,000 of them. And here's one, so these are just lists of integers. Now, I'm going to skip this. I'm also going to skip making the training RNN because I don't need it. This, I used a bigger RNN with how many hidden units? Whoops. Sorry. Ooh, 256 hidden units, so it's a fairly getting to good-sized LSTM layers. 2 layers of those, and also the embedding layer, which has much bigger vocabulary than before. I end up with quite a big system with more than a million parameters, a million weights in my network. So it takes longer to train. Also, I've got more examples in my corpus. I actually trained this for 5 hours on Google Code Laboratory, going up to 100 epochs, You can see I probably could have stopped earlier, maybe at epoch 60, but I didn't. I just let it go for 100 because why not? I wasn't monitoring it. You can just let it train further. Now, I'm not going to train it here because it takes 5 hours. I'll just load up my previous model. Okay, cool, load it up. Now we've got a sample from the model. Here's where it gets fun. So here's, I'm going to start with note 60, that's middle C. I'm going to sample 63 notes. I'm going to use the temperature 1, and it will then show a score. So here's my score, right? That's good enough, right? Just go home now. Should I play it? Okay, we'll play it back. Yeah, let's spin. Is anyone here a big Zelda fan? Yeah, there's a few Zelda fans. There's probably some more secret ones who didn't want to raise their hand. So maybe you'll recognize a bit of a Zeldic feel about some of these notes. But I don't think this is a very well-trained Zelda RNN. But we can certainly do a little bit more explanation by trying different starting notes and different temperatures. So here's a slightly different starting note. Instead of middle C, it's the D above middle C. Play this one back. Okay, that's a bit boring. Now, what should I do now? Should I change the starting note or temperature?
Yeah.
What should I do with the temperature?
Higher.
Higher. What should I enter to give me numbers?
5.
5. I think even if you don't know anything about music, this one looks weirder. Let's play it back.
Possible. I like it.
Can we go higher? Even weirder. Alright, I mean it's got kind of a grooviness to it, right? It's not completely without merit. How about we make a very low temperature and see what happens? 0.1. So this has really gotten stuck now. So it's learned something. Our network has learned something important, which is that often repeating the same thing is not a bad guess in any sequence. And so one of the more popular choices for its probability distribution would be just to repeat what happened before. So it's gets stuck now playing the 2 A's above middle C because we've just asked it to basically choose the most likely choice at each step. Yeah. Okay. I'll generate something long. 107. Give it a little bit of a boost here. It's good to get it to kick out of its comfort zone. Oh man, this one's gotten really stuck on F sharp and I have a high temperature. Now we're going to do some cherry picking here. I'll sample it again. It's done E. Okay. Now we get something which is sort of looks a bit more complicated. Wow, that's nice. I think that's the nicest thing I've ever heard this network do. So, right, that's the end of my lecture. You now get some time to relax before we start our workshop session, which is basically you hanging out with your groups and telling me what your project is going to be, and telling me what paper you've chosen to review, and telling me which of the next two lecture weeks you're going to present your project in, and then writing that information in the sheets. Okay, so I'll be going around asking these questions. There is pizza today at 5 o'clock. Yay! Pizza. Thanks, Iffy.
Okay, good afternoon. Welcome back. So today we're going to talk about deep neural nets, RNNs specifically. And before I start, how many of you have studied neural nets, just the classic version of neural nets? Okay, and how many of you have implemented backpropagation? Okay, about half. So what I'm going to do here is the first half of this class is going to be a review on how the classic backpropagation algorithm works and some intuitions, and then we're going to talk about convolutional neural networks and why they help and in which problems you can use them. Right? So just a very quick review. Everything here should be kind of obvious to everyone, I think. So like a classic problem that we have in machine learning is to predict a number, right? So imagine that you work for Facebook and you want to predict how many likes a given post is going to get. And you're going to try to predict that based on two variables: how many friends were online at the time when you made the post, and how funny you think the post is. And this is a number from 0 to 10, you just pick a number, right? So let's say you collect some information about 6 posts that you made in the last month, for example, and you measure the value of those variables, so how many friends are online, how funny you think the post is, and how many likes the post actually got, and you do that for 6 posts. In practice, of course, you would do this over like 1,000 posts or more. So it seems like there's a pattern relating how many likes you get and the number of friends and how funny the post is. Can anyone see what the pattern is? It's not completely obvious, at least not to me. But every time that I ask, there's one person that gets it. No? Alright, well, if you think for a few days or a few hours, you see that there's one way of trying to predict this from these 2 variables, which is just half the number of friends plus how funny you think the post is. If you use this equation, you get these predictions, which are almost correct. They're like you get this for this post, you get it's off by just 1, which is not terrible, right? So does anyone know what this is? What kind of machine learning model this is? This is linear regression, right? Does everybody know what linear regression is? So linear regression is a machine learning strategy that you can use to try to predict numbers like this based on other numbers like this, which is just a weighted sum of these variables. And what the algorithm does is to find the weights that you need to assign to each one of the variables. But in many, many problems, it's not possible to find a good prediction based on just a simple formula like this. And that's one of the situations where neural networks help us. So instead of doing linear regression, which is just this weighted sum, you can do some other complicated function that takes as input the same variables, but works in a much more complex way, right? And that's neural networks in a very, very high level way. So a neural net, as most of you probably know, is something that looks like this. It's like a sequence of layers of neurons. And you could train a neural net to take as input, for example, how many friends were online, again, funny level, and how popular you think the subject is. And essentially each one of these is a number. You propagate things forward in the network. So you assign, like, you measure these things for a few posts, and you propagate this forward, and at the end you get a number, which is a prediction. So like 0.7 likes, right? So this, I guess everybody knows about this. And you could train networks that are much more complicated. So you could train, for example, a network that takes as input a picture, and in this case the inputs would be the pixels of the image, and you could have many outputs. So the outputs could be interpreted as, for example, the probability that this image is an image of a cat, or a door, or a lion, or whatever. So in cases where you have to process things that have patterns, like images have patterns, right? Probably the color of this part of the fur of the cat is very similar to the color here. It's not completely random. So there is a pattern that, like, if these 2 inputs are close in the image, probably they have similar values here. So RNNs allow you to exploit patterns like that. And that's what we're going to study today. So a few applications, like these are novel applications of neural networks. Have you guys seen this? Deepfakes? This is a pretty weird application. I forgot the name of this person. Does anyone know?
Amy Adams?
Amy Adams, right. So like you get this random video of her, and then you train a network that you can say, well, I want to replace her face with Nicola's face. And then the thing automatically like changes this video and comes up is something like this. Which is pretty amazing in my opinion.
Wow.
So anyway, so you can do this with neural nets. So what is a neural network? It's a composition of many neurons. Like an individual neuron is something that looks like this. This again is probably nothing completely alien to you guys. It's a bunch of inputs, like 3 numbers. Each input is, you associate a weight, which we call theta in this case. And how does the neuron compute its output based on the inputs? It's just basically a weighted sum, inputs multiplied by the weights, and you pass that through what is called an activation function, which could be, for example, a sigmoid function. Looks like this. So you just take the weighted sum of the inputs times the weights, and you put it here in this equation, you get something out, right? In this case, a number for, between 0 and 1. There are other activation functions that each one has their own properties, but this is a popular one. So what you do then is, this is one neuron. You connect many of those like this. So each circle like this is just the thing that I showed. And does anyone know, like an intuition, why is it helpful to have many neurons in a layer instead of just one? What is it that these intermediate neurons are doing? If you if the task is to take as input an image, which could be anything, and let's say in this case that the goal of the network is just to predict what the probability of this image is, what is the probability that this is a cat? What is it that these neurons, how do they help? Does anyone know?
We can get more probabilities.
Of what?
Like, we would have more neurons, like in some neurons the probability will be high, in some neurons the probability will be low.
But the probability of what? That's the question.
You can look at different parts of the cat, not just the whole picture as one, but like one ear, the tongue, the mouth, and stuff like that. Maybe?
Yeah.
Like I wanted to say that with more than one neuron you can represent nonlinear relations.
But what does that mean exactly? It's not, it's correct, but yeah.
They can recognize different features of the cat.
Exactly. So everything that you guys said is right. The way that my intuition about this is that if you analyze the pixels directly and you're trying to compute this crazy gigantic function that takes pixels as its inputs and tells you the probability, that's really difficult. It's something that is really complicated to do. But let's suppose that we have these intermediate problems that are simpler to solve. Instead of trying to detect if there's a cat here, let's say you have a simpler model that can detect if there are pointy ears somewhere in the image. And there's another model that tells you if there are 2 eyes or whiskers or something like that. So that's essentially what these neurons are trying to do. They're trying to identify useful features that may occur in this image that are going to help you in this task of classifying this image. So when you train the network, you automatically assign, in some sense, these intermediate tasks to each one of these neurons. And the task, again, is for each one of these neurons to learn a feature, which could be like a characteristic, a property of the image, that may help you in the task of classifying it. So in this example, it could be, for example, if this thing helps, not working. You could have this neuron is a model that computes the probability that there are pointy ears somewhere, or a tail, 4 legs, or whiskers, or something like that. And now, the task of this neuron is much, much easier. This is the neuron that is going to make the final decision. Is there a cat or not? And making this decision based on this other higher level information about ears, tail, whiskers is much easier than just making the same decision based on pixels directly. Right? Does that make sense? Okay, so this is what a neural net does. Nice, this thing not working. All right. So how do you use a neural network? This again, it should not be anything too alien. You basically compute what is called the activation of each one of these neurons using the equation that I showed. So you get the activation of that neuron, this one, this one, this one, and then these activations are propagated forward to the second layer, right? And at the end you get a number. What do you do with that number? I mean, that's the prediction, right? Let's say you had an image with 3 pixels, or whatever you're predicting, you get a number out there. this prediction might be right, might be wrong. What exactly do you do if that prediction is off? How do you use that information intuitively to update the weights? And I'm not asking about like any crazy math, just intuition.
You figure out how wrong it is, and
Right.
then if it's really wrong, you adjust the weights a lot, and if it's just a little bit wrong, you adjust them a little bit.